Yes, it is about addressing the flexibility and the decarbonization of energy system and using the times modeling. And it is this project, this presentation is done and the work is done in context of the GIFT project, which is an EU funded project in the Horizon 2020 Research and Innovation grant. And the Center of Applied Mathematics is participating in this project. And I am currently a student in the master's program of energy system optimization, and this is part of my professional thesis. So I will start the presentation with the project background, then talk about why we are interested in islands energy systems and about the flexibility of the power system. Then I will explain about the case studies, which are 2 islands in the context of GIFT, before finishing with the conclusions and the lessons learned. And the project GIFT stands for Geographical Islands Flexibility. Its main objective is to decarbonize the energy mix of European islands. And this is done with allowing a high integration of renewable energy sources, which are invested in locally, and providing a visibility to the grid with the flexibility and the planning of the evolution of the energy system. It is also based on providing and developing synergies between the different parts of the power system while reducing the hydrocarbon-based energies. And this is all done to ensure a sustainability of solution and their applicability onto follower islands. And the demonstration sites are one of them located in Norway and one in Italy. And there are 17 partners participating in this project. So the islands are faced with many challenges, especially in terms of energy supply and economic development. In fact, they are are presenting a marginal market for energy supplier and of commodities and energy services. And this also implied, and the remoteness also implies high transportation costs to acquire these commodities, and also being always dependent on imports, either the fossil fuels or imports through their connection to the mainland. In addition to that, they are vulnerable towards, these territories are vulnerable towards climate change, and they face, they are the first one to face the coastal erosions, the property damages, and the higher numbers of cyclones. Despite this fact, we find a lot of opportunities, especially with the policy support of EU Clean Energy for All European Island package, and which includes an initiative for the islands, for the EU islands. And with their endowment in renewable energy and the cost competitivity of renewable technologies and with respect to conventional solutions, they have a natural sense to invest in these technologies. And last but not least, also to provide and showcase their commitment to international agreements like the Paris Climate Accord. And this is why it's interesting to develop island-specific energy system models and to consider also flexibility. So what is about flexibility? It deals mostly with the operation of the energy system and to provide an instantaneous stability and the long-term security of supply. So it deals with the proper functioning of the energy system also. And it is also about the ability of reliably and cost-effectively manage the uncertainty that is provided with the stochastic nature of renewable energies. And finally, to ensure it's also supporting the balance between the production and the consumption. And we find in IRENA's report from 2018, which focus on the flexibility, several enablers that straddle all the energy system. It can be solutions that are technical, like the storage, while it can store electricity during high production periods and release it during low production periods, which most of the time or often coincides with the high peak of demands. Or it can be a demand side management. So it's more a strategy about shifting the and the participating with the consumer about shifting the consumption from high peak hours to low peak hours, and it can also prevent benefits for the consumer as well as the grid operator. And finally, to develop synergies within the whole energy system, and considering the transport sector in it, and other technologies. And to move on now to the demonstration site. So one is in Procida, it's called Procida, it's an island in Italy, and it's a small one located in the Gulf of Naples, and you can see that it's highly dense and presents challenges related to grid congestion and high seasonality of demand due to tourism activities. It is connected to a nearby island through a submarine cable. The second one is in Norway, in the north of Norway, and it's a large island and constituted from a cluster of large and small islands, and it's less dense but also present challenges related to the limited possibilities of new grid connections. And as you may know, fish farming is really famous in Norway, and the fish farming is still using diesel generators nearby this island. And here to talk about the geographical location of islands, of the Hinnøya Island cluster. We see here that this represents the small cluster of island, and here represent Harstad community, which is the center of all economic activities at 80%. And the whole thing is the Hinnøya Island cluster. It imports its electricity from the whole cluster imports its electricity from North Pole, region 4. However, there are trades between Grytøya and Harstad, as you can see. And the gift solutions for flexibility, there are 4, but today I will be talking more about the EV electric vehicles and the charging stations. So about the energy profile of this island, it is mostly the energy mix of this island, and it's constituted at 63% from imported electricity. And this is a good news for especially that Norway has 96% of its electricity from hydro. So it is a low emission or free emission electricity, and is used on all the sectors on the island except for the fish farming to some extent. But the remaining of the energy mix, we see a high reliance on fossil fuel, and it's due to the transport sector, which is important in Norway due to its geology. So why is it interesting to study electric vehicle deployments on the long term? First of all, at a national level, we see that Norway is targeting 40%, up to 40% of emission cuts from the transport sector, and also is giving incentives like tax exemptions on registration of electric vehicles, and also wants to increase the taxation of using fossil fuel. So all of these are enablers to switch to electric vehicles. And with 43%, according to the Norwegian government, 43% of the vehicles that are sold in 2019 are electric vehicles, and we see this trend reflecting also on the island. As for the flexibility with the EV deployment, it is about the controlling the charging. And we noticed that there are 3 types of charging strategies, but in this project, and it's mostly the most advanced ones are with the active control or smart charging. And this project uses the grid to vehicle or unidirectional control. And it is about shifting from peak hours to off-peak hours and to release the stress on the distribution grid, but also to control and reduce when needed the charging power. So how can we translate this in times? The electric vehicles are modeled in as batteries, as storage batteries, and the chargers are regular processes. We need to implement the fuel economy and capital costs related to these technologies and the operational distance. Also to input future service demands related to transport and the mobility pattern, as we can see. And an additional thing is to input the future electricity prices so that we can reflect the switch in, from peak to off-peak periods of charging. And since the government implies a taxation of using fossil fuels, it is also implemented in the model. So here we thought that it can be done. What Times mod can be doing is providing a charging strategy. So it will choose the low prices period to have it charging, and keeping it out of reducing this charging or setting it to zero during high prices. But we see here that it had to charge, batteries had to charge again, but it is not bad since the electricity prices are somehow acceptable. And if we look at the load demand profile and EV charging EV charging, we see that there is a reduction of the duck curve, and this is mainly due to the load filling phenomena. And to move on now to the Procida Island, it relies really on imports from the electricity grid with a quite shy percentage of PV, and uses electricity in all of the sectors on this island. So this is why it was thought to exploit solar energy potential, but with the limitation of having a small surface of the island. So the solar PV panels will be implemented on the rooftops of buildings. And when implementing this in Times, it was choosing more to invest in public and tertiary buildings of PV deployment due to the economies of scale. And however, when adding storage to also more talk about flexibility, it was choosing the public buildings, but it had a good result in terms of reducing the electricity imports, and it reflects on the total imports with a decrease at peak hours. And now moving on to seeing an additional method to introduce this smart charging. It's here in Procida, it was chosen to model it as a demand, electricity demand, rather than modeling it as batteries. But it's also interesting so that we can see how it is done. So no investment costs were implemented, and the load was calculated based on the fleet dimension, which was taken from the Italian strategic plan for the energy system. So the number of vehicles that would be deployed, electric vehicles would be deployed, was calculated based on that, and also technical parameters and behavioral attitude of charging. And we can see that 80% in Italy of EV charging is done at the evening, and with the V1G scenario, switch the share of people charging or vehicles charging by switching the demand to the night with implementing a share of this vehicles participating in V1G. And now to move on to the conclusions and the lessons learned from these demonstration sites, we see that the flexibility and is linked with PV exploitation on Proshida and self-consumption, and production of electricity through the investment in and integration of local renewable energy. And also using storage technologies can enhance this flexibility. However, in Hinnøya Island cluster, we see it more about a cross-sectoral flexibility solution with the electrification of the transport sector, but it's really specific to Norway because their electricity mix is constituted of 96% of hydro. And so that's how they are integrating renewable energy in their system. And to talk more about, and this leads us to key takeaways that we can take. Firstly, we should not only assess the energy system, but also the context of energy of the island when talking about these territories, because they are faced with constraints, environmental constraints, and location constraints. Also, flexibility is linked to investment costs and maturity of solution. This is especially with, for example, the charging stations. Their investment is higher is still high and during this period. And with the EV, more and more EV deployment, their cost may go down. And long-term planning supports the decision-making and new investment flexibility, but it is limited from a grid operation point of view and also from the data availability, so that with better data, we can see that in the Hinnøya model, the time slices were on the hour, however, and in Proshida, they were more about periods of the day, and this is mainly due to the data availability. But with the collaboration of different partners, this can be enhanced. And also there is a necessity of involvement of the consumer to become prosumer and participate in the energy transition through the flexibility solutions. So even not only investment should be made, but also encouragement to the consumer. And the permissible regulatory framework, we noticed that it should be implemented so that all of the IoT, Internet of Things, have their regulatory forms accepted, and the communication between the energy systems and the consumer to be able to provide a sustainability to these solutions. And this here you can see the references. And thank you for your attention. And I'm available for all of your questions now. I cannot hear you.
Thank you very much for your presentation. I cannot see any questions or comments in the Q&A. It's possible to write questions there, and if you are not able to answer them during the presentations, then it's possible to get answers later on from the presenters. I have one question. Did you do any sensitivity analysis on the electricity price, both on the level of the future electricity price and on the variability?
Yeah, actually, it's now I'm thinking about doing that. Thank you for I was thinking about that because now it's more about the development of the recommendations. So it will be very interesting to implement and study.
Okay, thank you very much. Then we will move on